Welcome back to the bunker. I'm Mr. Voppel, and today we're going to learn about normal force. But before we do, pause and grab your mission sheet. I'll see you soon. Ready? So what is normal force? Well, let's look at our facts. Normal force is the force of a surface on an object in contact with that surface. So to have a normal force, we need two things. The first thing we need is a surface. And what's a surface? Well, a surface is just any flat area that we can touch. This table is a surface. This wall, surface. This wall, surface. Floor. Yep, it's a surface. Any flat area that we can touch is a surface. So let's pick one. Table. What else do we need to have a normal force? We need an object. Let's see if I have something. Oh, here's my lab cart that I always carry with me at all times. Here's our object. So the table is our surface and the lab cart is our object. The only thing we need is for them to be in contact. There you go. Normal force is the force of a surface, table, on an object, lab cart, in contact with the surface. Well, there we go. Here's my next question. What direction is the normal force, or the force of the table on the lab cart? What direction is it? Well, what do our facts say? Our fact says that the normal force always acts perpendicular to a surface. Perpendicular, what does that mean? Well, good thing I also always carry with me this here perpendicular detector, brought to you by Expo. And what this perpendicular detector does is you just place it on a surface, like our table, and it points in the direction perpendicular to the surface. So here we go. What direction? Straight up. That is the perpendicular direction to the surface. Because all perpendicular means is straight up at a 90-degree angle away from the surface. So the question is now, what direction is the normal force of our table on our lab cart? It's straight up. The table pushes the lab cart straight up because the surface is right here and the perpendicular direction is straight up. So there you go. Now what I want you to do is I want you to draw a free body diagram of this lab cart sitting on the table, and it should have the normal force on it. Ready? Here we go. Welcome back to Mr. Voppel's Physics Toy Reviews. Today we're going to be playing with the motion detector and a lab. Oh, sorry. That's for a different video. Anyway, where do we leave off? That's right. Normal force is the force of a surface on an object in contact with that surface. So the force of the table on the cart is the normal force and it points straight up. Now my question to you is, can we figure out how much that force is? How many newtons is the force of the table on the lab cart? Let's see. Well, one thing that can help us is if we know the weight of the object. We know how many newtons it weighs, the force of the earth, gravity pulling on it. And to do that, I've got my handy spring scale, and so I will weigh this, and let's see, we get a weight of, see that, 5 newtons. So the cart weighs 5 newtons. Let's see if we can figure out what is the force of the table up on the cart. Here's our cart sitting on the table, and we know the normal force points straight up. And to figure out how many newtons that is, we need to answer this question right here. Is the cart in equilibrium? Yes or no? And so I want you to pause, answer that, and tell me how you know that it's in equilibrium. The next thing we need to do is write a net force equation to solve for the unknown normal force. Now we can write a net force equation in the vertical direction this time because we know there aren't any left and right forces, so that doesn't help us. So let's do this together. Let's write an F net equation in the vertical direction. So what would that be? We know that in the vertical direction, F net is equal to all of our up forces minus all of our down forces. And what are our up forces? Well, the only up force is the normal force, the force of the table up on the cart. So let's put that in there. What about down forces? Are there any down forces on the cart? Well, yes, gravity. The force of the earth pulls down on the cart. So let's put that in. So now we have a net force equation. F net equals up forces minus down forces equals the normal force minus the force of gravity. Well, to solve this, we need to know something else. What does Fn minus Fg equal? Well, when an object is in equilibrium, what do we know the net force equals? It always equals 0. In equilibrium, F net equals 0. So we can say that. So now that we have our net force equation, let's use it to actually solve and find the unknown normal force. So let's move it up here and let's see if we can solve this guy. So we have Fn minus Fg equals 0. Do we know what Fn is? No, that's our unknown. That's what we're trying to find. Do we know what Fg is? Yes, that's the weight of the cart. We know that the cart weighs 5 newtons, so let's plug it in. So there you have it. Fn minus 5 newtons equals 0. So go ahead and solve for Fn. Well, there, Fn equals 5 newtons. The normal force is 5 newtons. The table pushes up on the cart with 5 newtons of force, equal to the weight. And that makes sense. After all, the cart is in equilibrium. Up forces equal down forces. Well, there you have it. Fn, normal force of the table on the cart, is 5 newtons. But how do you know I'm not just making that up? If only there was some device we could use to measure normal force. Oh, what's that you say? On our facts, it says that normal force is measured with a platform scale? If only I had one of those. Luckily I do. Here's a platform scale. Wow, so here's what we're going to do. Let's put our cart on the platform scale, this force plate, which is going to measure how much force this plate is pushing up on the cart with. And let's see, is it 5 newtons? Well, look for yourself. So as you can see, here's our platform scale. What it's going to do is when I hit go, it senses how much force it's pushing up with on whatever is on top of the scale. You can see on the side of our graph, the vertical axis is measuring newtons, and then the horizontal axis is telling us over time, at what point in time, how much force it was pushing up with. So you can see when I hit go, and there's nothing on the plate, what does it read? 0 newtons. You can see it bounces up and down a little bit, but it's right around 0, which makes sense because there's nothing on the force plate. So that makes sense. Now instead, if I take the force plate and I go and I push my hand on it, you can see that it registers however much force the plate's pushing on my hand, the normal force of the plate on my hand. That's how a force plate works. So now let's use that to see how much the normal force is on our cart. So let's bring our cart in here and we're going to put it on the scale and see what it reads. Now before we put it on, when we start, it's at 0. What happens? Well, look at that. Right when we put the cart on the scale, it reads, you can see it's bouncing around right around 5 newtons, which is the normal force, the force of the scale on the cart. We got it right. So maybe you're thinking, come on, Mr. Voppel, that's easy. I knew that as soon as you asked. Of course the cart's in equilibrium. 5 newtons of the earth pulling down and 5 newtons pushing up. The normal force is 5 newtons. Okay, smarty pants. What if instead of this 5 newton cart, we use this 10 newton weight? What about that? If I set this 10 newton weight on the table, what is the normal force? The force of the table on the weight. Well, this time, let's do it again. Let's take our weight and we're going to put it on the scale and see what it reads. What is it? Oh, you guys are too good. It's 10 newtons. So the normal force is 10 newtons. Okay, so maybe these were a little easy. Normal force is 5 newtons. Normal force is 10 newtons. Okay, well now that you got that down pat, I want to see if you can tackle some more difficult problems, starting with this one right here. See ya. Starting with this right here.